So this is just me documenting my learning sort of experience about openGL. Currently I'm learning openGL, so this is just sort of a revision because I've learned how to draw a triangle, but I'm gonna do these things again today, so let's see. So currently I'm using Ubuntu 20, I think it's 24.4 LTS, and yeah, I'm actually currently using this following this tutorial. I'm going to provide that in the link. So yeah, so basically let's get started. Mm, image, image, introductions. Basically, what you need to do, like prerequisite. Basically, you can just simply, like, in my opinion, you can follow it serially. But since I've already done that, I'm going to directly jump into drawing a triangle. Firstly, I'll first thing you need to do is to create a window. So that's one of the main things you need to do, and you can do that. 11. Yeah. So you can firstly do that with how I'm currently doing is I'm using GLFW. So you can do that, and how I'm going the text editor I'm using is Emacs. So yeah, and to set up a window in GLFW, I followed a tutorial on YouTube. That's like when you search how to follow, how to draw, how to build a GLFW in Ubuntu. The first video that you get, that's the one I followed, and I'm going to provide a link for that in the description as well, so you could follow that. It's just a documentation process of me just trying to learn OpenGL and me just seeing how things are. So yeah. So in directory, let me just create a new directory for that. Hello. Well, it's just going to default GL stuff. Gonna create a new directory, name it. So the language I'm gonna be using is I'm actually gonna use C, but I'm gonna compile the file as C++ because at times I might need some C++ applications which uh, will be used later on. So yeah, I'm just gonna name it .cpp. So yeah, let's go to GLFW's website to see how they initialize the front page. Uh, I don't know, and it's a bit slow. Damn. Yeah. Okay, what to just do is just copy the stuff. It's Control Y. So if I need to explain this stuff, then basically what this is after you compile the GLFW in your local device, you need to just include the necessary header files, and I think this one is for all the initialization purposes of the Windows, and also the poll events and the input events and all the necessary files that will be used. And I don't think any other GLFW header files are gonna be included later on, so let's say maybe. So after that, inside the main window, what we have is we have a data type that is GLFW window pointer. This is a, I guess this is a custom data type. I know this kind of stuff, but to my, I think I don't know if it's true or not, but there's a custom GLFW window pointer data type that just has a variable named window. Uh, then we are going to initialize the GLFW using GLFW init. So yeah, there's that. Then just return 0, or return -1 it does not if it does not get initialized. So yeah, that's that. After that, there's the window, and here, yeah. Now what this returns, like what this glfw create window returns, is a pointer, a pointer to this data type. Like, uh, this may be programmed to return. It is just a pointer to a certain block of memory that's been allocated by doing this glw create window, and all these are the necessary data that's inside it. And later on we're going to use that data to specify what the screen width and screen height, and like the name of the name of I don't know, the window is. Like, yeah, you can just change that. You can add your own. I normally do constant and screen width to, I don't know, 1080, constant and screen height goes to 720. uh, Screen width, screen height, I don't know, hello window. I know. And the other two, no, the two parameters, let's see. Create window reference. That blue should have gone to the first link. Hmm. The window, what are, I don't know, man. Maybe it's just something. Just leave it null. They didn't. I don't think they've bothered to specify what's the parameters for those. No, no, no. I think, yeah, this one's for if you, in case you have another monitor, I guess. Hmm. I don't know. Just leave it at null right now. We don't need it right now. So yeah. If is not window, okay. If window is not initialized, then glfw terminate. It says for itself. Return 1. Yeah. What this does is just makes the window. I know maybe you can specify many windows, but this just makes that current window the thing we are going to focusing on, and not the other things. Yeah. So that's my dumbed down version of what I understood. Anyways, yeah. So this is the main loop where you do all your rendering and all your update stuff. Yeah. So this is one of the main things, and I don't know. This is like the heart of the program, I guess. This is where everything runs. This is the source. I don't know, yeah. The clear color. But before you draw into, before you draw like anywhere, first of all you need to just clear the screen out. Like, just keep it as a blank canvas, and then you can draw on it later on. So yeah, that's just what it is. Gel clear color. I know. I think you have. Let's see. Hello window. I think there's a function using glfw to draw glf uh, no, I don't think. Let's just leave it, doesn't matter right now. glfw swap buffers. So I don't know much about this stuff, but what I what I sort of know about is it is like there are basically two windows that uh, swap with each other when something is to be displayed. Like the first screen displays the stuff that's to be displayed, while the second screen is receiving the data that is to be displayed next. So it's a continuous process of just swapping between the windows while one waits for the uh, necessary information to be displayed while the other displays it, and after it finish after it completes its display, it goes back and the other comes front. And the other in the sense like the one that has the complete display information comes front and the other goes back and it gets filled with the information. So yeah, that's that. And GLFW poll events is it's another GLFW function where it takes the inputs and all the events, like it handles events like input events. I don't know, I just remember input events. I don't know if it's used for other events. It might. It. I think does use other events, but right now I only know GLFW poll events. It takes input events, and this is one of the input events. Like GLFW window should not close, passing the pointer window GLFW window pointer as its parameter. What this says is like until the window is not closed, just run these things. Just run it. Do not close the window. Just run these things infinitely or until the battery runs out. I don't know. Yeah, after that you terminate the GLFW. So remember you initialized it here, so you need to terminate as well, and yeah, return 0 is that. Now what another thing you need to do is uh so yeah, I just press G to update that in case you don't know. And now what you need to do is in order to run this you need to include many static libraries, like link them at runtime or just passing them in the terminal. I don't know, but you need to link them while compiling. Yeah. So in the provided videos link where you initialize the GLFW, he has also provided all those things, all those libraries that need to be linked at the end. So, and I've already done that. So I'm just gonna create a make file. You can also create a batch file, or no, not batch file, but no, shell script, I think. Yeah, or you can just manually type it in the terminal, but I'm gonna make a make file. It's not a complex make file, it just does the bare minimum stuff here. So yeah, uh, I have it stored somewhere. Wait a minute. Cube make file. Yeah, so this is the thing. You compile it G++ using a C++ compiler and include all the necessary libraries later. And then this minus G is for in case you need to debug your file using the GDB, because it creates a I forgot what it creates. It creates a debug file, I think. I don't know. Forgive me. Just copy that and go back to your main directory GL stuff, I think. Yeah. Uh, just paste it out here. Yeah, yeah, yes. Yeah. Just paste it out here. Update that stuff. Create a new cdgl stuff. Just compile it and slash and yeah. There's the window using glfw. Nice. It's not that pretty, but it's getting so good. getting somewhere. Let me create a runnable minus o run. Yeah, and let's run. Let's run. Yeah. Anyway, now uh, I think in order to run OpenGL, so in order to run OpenGL like functions, you also need a library that's called Glue. OpenGL extension wrangler. Like what it actually does is like when you use OpenGL functions in your program, uh, at compile time, those functions require I don't know I don't know this stuff in much depth, but they require a function pointers. OpenGL function pointers they require which I know which is used to connect OpenGL native functions to some values. I think those kind of stuff. I don't know much about that, but yeah, it's uh, let's just see. Why do we need blue? Yeah, basically this is the thing. If you link, it must exist on program mode on glue and you're not linking the GL functions directly. Yeah, that instead getting function pointer after initializing. I should check it runtime used. Yeah, it is used for linking purposes, I guess mostly. I don't know in much depth, but you do require that, or you can just manually do those things. But as the program grows, you won't be able to keep track of everything manually. So glue does that for you. So yeah. You also need to initialize glue. I think. Let's see. Uh, glue. I think this is how you initialize it. Glue. Let's see. I think it's out here. Yeah. Mm, just using glad. Glue. So include glue.h. Mm, no, I don't think. Yeah, this is how you initialize. I don't know why they put the glue experimental, but I think it does something. So let's put that glue experimental. Hmm. So I think uh, should initialize glue after after this one. Let's see glue experimental. Glue experimental equals to GL true, and if is not glue in it, this is how you initialize glue. Uh, is not equal to glue. Okay, I think. No, I don't think it's glue. Okay. Uh, how to glue in it? Glue in it. Mm, yeah, is not equals to blue. Okay. What to say? Uh, just write failed to slice glue. You just need to include the standard input output of C after that. stdio.h. Let's see if this runs. Clear make. No, I included the wrong GL glue. Whoa, what was that? GL, um, do we need to include this first? Clear make. Yep, yep. Failed to initialize glue. Wow. What's going on here? Okay, so I'm gonna do this at the end. Here, initialize glue. Initialize CLFW. Damn. Clear make. Did I save that? I think I did. Okay, okay. Apparently it's running. So just leave it at that. Close these things. Let's get started. Yeah. Now we can run. Now we can build this stuff. Hello triangle in openGL everything is 3D but the 2D. So yeah, basically what OpenGL has is it has this graphics pipeline. So a pipeline, basically what a pipeline is it's just a, a number of a number of things that is to be done to a certain stuff is done sequentially, and at the end of the pipeline comes out a product. It's just like, I don't know. In he has also given the example about car manufacturing factory, like at each stage something is added to it, like something of importance which is not added by the other segments, or the boxes parts, which is then later on uh, compiles becomes the final product. So yeah, that's just what he's trying to say. Takes input of 3D transforms to this 2D colored pixel, can be divided in several steps where each step's required output of previous step as its input, highly specialized and can easily execute in parallel. Hmm. Dependent on thousands of processing CPU shaders. Process core runs small programs on forest planners. Shaders. So shaders are basically programs that run on the GPU. GPU is highly capable to run multiple parallel operations concurrently. In the in the sense, like, it can do multiple things at the same time, multiple different things at the same time, and output them subsequently at the same time. You know, in that case, it's much powerful. So some shaders are configured. Shaders are written in OpenGL. Yeah, GLSL, and note that the blue section of library can inject our own shaders. So what it's trying to say is like these blue boxes are the segments sections can be uh, that can be edited, or that provides us with the power to be able to influence the things that currently happen in those sections, like in this gray areas, or these gray stages. We cannot do anything. It just simply takes an input and does its stuff and throws an output. We cannot further proceed to do something with it. So yeah, that's just it. And the first stage is the vertex shader, and after that it's just vertex shader is just takes the in vertex shader it just takes the coordinates of the final output, and in this case, where as seen here, we're drawing a triangle, so it's taking the coordinates of a triangle. Then after that, it's just assembling the shapes, and after that, it's geometry shader. Shape assembly is it's connecting the dots, I guess. Geometry shader is, I don't know, it's just figuring out what that is, I guess. And rasterization, I guess it's trying to divide divide the shape into small boxes which can be later passed on to the GPU, where each box can be filled with a certain color here in the fragment shader, and then later on tests and blending. Uh, Further operations could be performed on it. Yeah, as you can see, the graphics pipeline contains a large number of sections, fully rendered pixel, and explain each part of the pipeline simplified. Okay, so there's going to be basic explanation about the pipeline. Mm, as input form a triangle in an array called vertex data state. Vertex is a collection of data per 3D coordinate. Yeah, the vertex data is represented using vertex attribute that can contain any data point. Like, but for simplicity's sake, let's assume that each vertex consists of just a 3D position and some color value. Okay. The first part of the pipeline is vertex shader. That takes as input a single vertex. The main purpose of the vertex shader. 3D coordinates into, yeah, it's just saying that it's just transferring the coordinates into the 3D coordinate space. Just like when we pass the coordinates, we sort of know that it is a 3D coordinate and how the final image should appear to be, but the computer doesn't know that, so it's trying to pass those coordinates. It's just trying to make sense about those coordinates, I think. Anyways, the output vertex is optional passed to the geometry shader from generate the shapes. Oh, yeah. So geometry shader, like using those vertices, it can also generate some other shape using those vertices. So it's just trying to say that it can generate a second triangle out of it, same shape. Yeah. Anyways, the primitive assembly stage takes all the vertex GL points from the vertex shader. It's just something. Output of the geometry passed to rasterization stage, where it maps the result to the corresponding. Yeah, in the rasterization stage, so maps the necessary pixel to the defined window, to the window that we have defined. It maps the pixels to that window, corresponding window to use. Yeah, clipping is performed. So what clipping is, like, if if a coordinate is outside the view space, or it's outside the window that we have just created, it gets clipped off. That means it the data is never actually rendered. Like, it just gets deleted, or it's never used, just gets ignored. So yeah, the main purpose of fragment setter calculate. So yeah, calculate the final color of a pixel, that is usually the stage where all OpenGL effects occur. Hmm. Calculate the final color that's used on stage. Usually the fragment shader contains data with 3D scene. Okay. So fragment shader is the place where all the visual representation stuff happens, like all the colors, shade, shadows, lights, and I think the blendings as well. So fragment shader is responsible for all those things. Okay. After that, responding everything determined. Mhm. So I know this is just a basic description about the graphics pipeline. It's actually much more complicated, but yeah, I think I gotta study a bit more on that. But right now, to be able to start right now, just having a basic understanding of this stuff is, I think it's good enough to start on, and later on you can just arrive and just study those things. And that's enough for me as well. Later on, just come back and study those things properly, because later on you actually need that, or you won't be able to progress further. So now we're actually starting to see the codes. Wait a minute. Hmm. So vertex input, to start drawing something we have to, so yeah, this is basically, doesn't simplifies coordinates. It is a specific range. So what this is saying is that everything is in the range between -1 to 1 on all three axes, x, y, and z. Coordinates within so are called normalized device coordinates will end up in your screen. So to render a single triangle, we want to specify a total of 3 vertices with each vertex having a 3D position. Float array. Uh, okay. Mm, I don't know, let's just make it out here, I guess. Increase the font a bit. Float vertices. Uh, let's just create a triangle like this. You can sort of see how the coordinate is laid out, and according to that you can see how you can design a triangle. You see, if you want to draw a triangle that's like this, let's just draw something a little different. The coordinates should be -1 0, -1.0 x 0.0, -1 x and 0 y, and the 0 in the z axis, and it's going to be 0 in the x-axis, 1 in the y-axis, and it's going to be 1 in the x-axis, I guess. 0 in the y-axis and 0 in the y-axis. So yeah, after that, z-coordinate vertex data define send input to the first process of the graphics pipeline with vertex data defined. Send it as input to the first process of the graphics pipeline. The vertex edit has done the creating memory on the GPU. Store the vertex data. Hmm. This vertex data will send it as input to the first process of the graphics pipeline. Memory on the GPU will store the vertex data. Configure how OpenGL should interpret the memory. Vertex data is then processed. We manage this memory via so-called vertex buffer object. Store large number of vertices in GPUs. So so what GL What VBOs are used for, uh, according to my understanding, is that first you generate a buffer and to it pass the address of this unsigned int VBO where a certain address is returned, and uh, in that address uh, all the buffers in the sense like all these vertices, it's just stored out there, and it's actually stored in the GPU. So vertex shader has quick access to it, and the VBOs generally store as much buffer data in the GPU as they can, so that vertex shader has relatively very quick access to it. Like, that's just what it says here according to my understanding. So to generate to create a VBO, first you need to specify an VBO by using an unsigned integer variable data type. Then you need to generate a buffer using GL gen buffer or buffers. And the first parameter is it's not the address or anything. It's just telling like we are generating one VBO. That's just it. It's nothing else after that. So yeah, GL bind buffer. After that we bind the buffer to GL array buffer. So what GL array buffer is like uh, in that buffer just consists of an array of data, So yeah, that's that array buffer, and we pass the VBO. We bind that we bind that array to that VBO location, and we pass the data buffer data with GL bind buffer data. Our first parameter is the type of buffer, which is GL array buffer. Second is the size of the data, which is size of vertices. The third is the data itself, vertices, and the fourth is yeah how that is to be drawn later on by the vertex shader. GL static draw. Target data into currently bound. Its first argument we want to copy vertex data currently bound. Target into pass the button. Fourth parameter specifies how graphic card. Yeah, it's how we want the graphics card to manage the given data. There are three forms. GL static draw. It says it draws one and use the GPU at most few times. So the most, I guess, the useful one among them is GL static draw. Like how we want to use that. So the GL set only once and used many times. GL dynamic draw that has changed a lot and used many times. In case in future when you want to draw something like the vertices are constantly changing, so you can use dynamic draw in those cases. It's what I thought I would be doing, but I've actually never used it. So yeah, just use GL static draw. Okay, so this is the first vertex buffer that's been created. Vertex buffer. Uh, After that, so what what exists in OpenGL is you also need to be able to write the vertex shader and the fragment shader yourself, and during compile time it's going to get compiled overall, like it's just going to get compiled everything together. So in that vertex shader you need to specify how you want to manipulate those coordinates that you have passed in the vertex buffer object, So yeah, this is just trying to say that. And let me just explain what this code does here. So first line is for the version of GLSL that you are going to use is 330 means it just placed a point after the first integer, so it's basically version 3.3, and the core means it's using the core GLSL functions or functionalities. So yeah, that's GLSL core. Layout location 0 in vec3 pose. What this actually is like, it's going to be defined later on, but I'm just gonna tell it to you. Like, when whenever you pass a vertex buffer object, like you just pass it, and it's been said that the vertex buffer, like after you generate the buffer and bind the buffer, it quickly sends the data to the GPU's memory as much as it can so that the vertex shader can use it. But when you are drawing or when you are using that data, how do you actually know which buffers to use? Like, how do you know that? How do you even have control over which buffers to draw, what to use? So, to answer that, this thing out here, later on, there's also stuff I'll explain it again, but for those, for to be able to map the vertex buffers, you need this line out here. It's just a layout location equals to 0 in vec3 equals. So what this is just telling is in location 0, just in that location include a vector 3 a position. So remember when we specified those values in a row like order with it consists of just 3 columns. So yeah, this vec3 is just for that purpose, just 3 values at a time, in vec a pose. So inside a void main, uh, GLSL is sort of similar to C, so consists of a main function inside which all the operations run. So inside it there's a GL position, GL position is basically the final position in the vertex shader that it's going to align it to. Like, remember you read like it's going to align the 3D coordinates to the 3D coordinates. So this is just that. It's just aligning those values to the 3D coordinates. Vec4 consists of XYZ value, and I think it's alpha value. It's not alpha, it's not color. And I think location, it's a W. Yeah, it's W component. Uh, I think it has something to do with later on. There's something to do with. I know it's a W value. Just leave it at 1 right now. GLSL is similar to C. That's what I said. And yeah. So this is how you define a vertex shader inside your code. You just passed a constant character pointer to the first element of that string, and it gets parsed as like a file. So yeah, that's how you define the shader. And just let me write the shader. Where should I write it to? Constant. Let's just write it out here. Normally, you need to also enable error checking while compiling. No, it's later on. Let's just write this vertex shader. Vertex shader equals to, man, normally it's so frustrating to write the shaders because normally it doesn't work as you want it to when you write it like this. As version 330 core, I think you need to do this stuff. Yeah, as vertex layout location equals to 0 in vec3. Let's just write a position. You don't need to write exactly what's out there. Vec3 core void main. slash n slash input plus wait a minute, and there's GL position, right? GL position equals to big 4, and it just can do that. Pose x pose y pose z 1.0 slash n slash. Let's close that. Yeah, I think it's going to work. So yeah, we just wrote our vertex shader, and now we need to compile that shader as well. Interesting, right? You need to compile the shaders before you compile the entire program. See, that's pretty good, right? So how you compile this is, first you need to, everything in like OpenGL seems to be just a transfer of like a communication between the GPU and the CPU. You know where things about where things are and how you are supposed to do them. In that sense, first you create a variable vertex shader which is unsigned int. Then you pass the GL create shader and pass the parameter GL vertex shader. So yeah, let's do that. Compiling vertex shader unsigned int vertex shader vertex shader, and I need to wait my dog as well. GL compile shader, GL vertex shader, right? GL vertex shader. After you compile that, you first need to create a shader, not compile it. Create shader. Provide now the each. Now we need to pass the shader source. Only then can we compile. GL shader source vertex shader. We are in the GL shader source. We are first passing the pointer where a shader block of memory, I guess, is created in the GPU for the vertex shader. So we first need to pass memory address of that buffer data, that memory that's been created, and secondly we need to pass, what's the second argument? The second argument, yeah, how many? It's just that. And third is vertex shader source. That is the source. Specified src as well. Vertex shader source. Vertex shader source, and fourth, let's leave it null. I guess it's something to do with legacy. Now we can compile shader. Vertex shader. Just pass the memory address and just compile. Oh, we also need to check if the vertex shader has been compiled successfully or not, because you can never know. You can just always get a blank screen, and you can never know if it's in the there's a fault in the vertex shader, or there's a fault in the fragment shader. You can do that. Um, I don't like to write it, so I'll just copy it, I guess. I don't feel like writing it. Error checking. First tab. Where did it go? Yeah. Control Y. Hey, it's an STD, so let's just write it in printf. Vertex shader could not be compiled. I think it's percentage f for that info lock. Yeah, let's see if we can run it. Clear. Yeah, apparently it runs. Okay, we are already getting an error. Unexpected identifier. Hmm. So what am I supposed to do? Am I supposed to do this? Make. Nope. I think it's this. Uh, um, uh, Normally how I write this is scrape it all off. I'm gonna write it in a single string. What? Where do you want something? Here. Hmm. Okay. It's running successfully apparently. So yeah, that's just the vertex shader. After that is the fragment shader. So fragment shader is the last stage in the graphics pipeline, as you have already seen above, or in case you don't know, it's the last stage. Second final shader we are going to create render time. So everything that's going to be visually displayed on the screen is controlled out here in the fragment shader. Keep things oranges color. So yeah, to explain this code, this is a openGL shading language program. So to explain this code first, we've included the version that's 3.3 using the core functionalities, and this is the output of the fragment shader with for frag color. Frag color is used. I think it's built-in data type. I don't know. It's something variable that controls the output color. Frag color, and currently when we include this, like this is the RGBA format, and when we include one red, half green, and 0.2 blue with full alpha channel, full alpha value, we get an orange color. So let me just write the fragment shader in that format as well. Fragment shader source equals to, and if you can write a, if you if you find yourself writing this in better in the other form, you can do that, but I don't think. No, it's not an output variable, it's just an out vec4, and out vec4 normally consists of, I guess, the only thing that's the RGBA values. So yeah, it's not a built-in data type or anything. And the other thing, like if you find yourself getting a lot of troubles in to compile these shaders, just write them in a single line as me, like me. It's more easier that way. Later on, you can write these shaders in a different file and include them. but that's for later on. So yeah, frag color equals to vec4 1.0, 0.5, 0.2, and 1.0. And these are the coordinates. And now we need to compile the fragment shader as well. Fragment shader. Yeah, it's similar to vertex shaders, so you can understand it, I guess. It's similar though. First we create a vertex shader, then to that shader we pass the necessary details about the view, that fragment uh, fragment shader code, which then uses that to compile, not even compile, to see how to output the final image. So yeah, fragment shader, transcendent fragment shader, GL, no, fragment shader is GL create shader, and first we pass what kind of shader is that. So it's a fragment shader, so we pass that fragment shader. GL shader source. In fragment shader, we pass the shader source only one string. Shader source is fragment shader source, and last we leave it as null like before. Now compile the shader. Compile shader fragment shader. Yes, yeah. That's how we do that. Compile the shader. Let's see. Also, we need to error check, so you can just copy paste that and pass fragment shader in here. Success 1, log 1, success 1, it's fragment shader info log 1. Let's see. 11. Okay, let's see if it compiles. Compiles headers. Where is that? Ah, compile shader. Slash run. Yep, both the shaders are working. Now let's just do this quick, okay? The last part of it. We are at the last part of it. I think we are sort of at the last parts of it. So after that, after we compile both the shaders, we need to create a shader program that is finally linked version of that is consists of both the finally linked out total vertex shader and the fragment shader linked versions. So we need to do that. Compiled, link them. Uh, 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 let's just do that. Program. Shader program equals to GL create program. Let's do that.